afternoon. Why don't you speaking up with me again? Can you hear me?
I'm having a big problem with the math. Very big problem.
Okay, Horace. Do you have the paper in front of you?
Yes, I do. I have the last handout, and I have the one
Yeah,
that,
it keeps trying to connect to your computer, so just turn your Bluetooth off.
How do I do that?
Go to your settings.
Finder?
Okay, Horace, hang on a second here. Okay. Horace, I am looking at this page. Is that the same one you're
that's the
looking at?
same one. Yeah, that's the one I'm
Okay.
talking.
Okay, follow me on this. On the left-hand side, underneath example, I give you the frequency of 5.4 times 10 to the 17th power. That's a very, very high number. And the question is, what's the wavelength? Everything is referenced to the speed of light, which again is 3 times 10 to the 8th meters per second. So you're going to put 3 times 10 to the 8th in the numerator. And then you are going to divide that by 5.4 times 10 to the 17th. Now, Horace, it's been a while since you've been a student, and I understand that completely. So I'm going to show you a shortcut of how to do that particular kind of math. It's not complicated.
Yeah, I have my calculator here.
Well,
It's just
hang on a
simple.
second here. You've got 3 times, no, write it on a piece of paper, okay, so that you can actually see what I'm talking about. Put 3 times 10 to the 8th in the numerator and divide it by 5.4 times 10 to the 17th. You're going to solve this problem in 2 easy steps. You've got your calculator in front of you. Step 1, divide 3 by 5.4. And what's the answer? Are you plugging it in, Horace?
Yeah, so I'm going to
It should
divide.
be, it's like
Uh,
0.6 something.
Yeah, but okay. Divide 3 by
Divide it
5.
by 5.4.
Okay, and I got a 0.6.
That's about right. So on the other side of the equal sign, you're going to put 0.6. You're not done yet, Horace, but you're going to
Okay.
put 0.6 there.
Okay.
Now you have to deal with those 2 10 numbers with the exponents. The top one is 10 to the 8th.
Okay.
The bottom one is 10 to the 17th. There's a very simple rule in mathematics, Horace. When you go to multiply or divide these kind of numbers where they have an exponent up there, because we are dividing, you are going to take the number 8 and you are going to subtract 17.
Okay.
And
Subtract.
you are going to come up with -9.
Okay, yeah.
So
Okay.
your answer on the right-hand side of the equal sign is 0.6 times 10 to the negative ninth power.
Times 10.
Okay.
Negative 9. Okay, I got it.
Now, the other part of the, and keep in mind, Horace, this is all examples. You're not going to do this on the next exam. You're not going to have to do this math.
Yeah, but it bothers me when I see it here and I don't understand it, what I'm looking at.
Okay, no, and I trust me, I admire that, Horace. That's why I have no problem going over this with you. So far, your answer is 0.6 times 10 to the negative 9. That is correct. But in the example, I'm asking you to convert that number into micrometers. And here's how you do it. To give you an example of what you are about to do, essentially I'm asking you to convert, say, for instance, 2 feet into 24 inches. So that's what we're about to do here. If you look on the number line,
Okay.
a 0 in the middle, and on the left, there's 10 to the negative 3, negative 6, 9,
Yes.
all that. You see that?
Uh-huh.
Under your answer is 10 to the negative 9. That means that your answer is 0.6 nanometers. That's what 10 to the negative 9 means, Horace, nano.
Okay.
So,
I see up top you had giga, but it's nano.
well, 10 to the negative 9, look at the left-hand side of that number line. Underneath
Okay.
10 to the negative 9, it says nano.
Okay. All right.
Or on top of that number,
Yeah.
it says nano. Okay, in the world of mathematics, Horace, anytime somebody uses the word nano, they automatically mean 10 to the negative 9.
I got it now.
Okay, so that's more precisely, the answer we came up with was 0.6 times 10 to the negative 9, or you could pronounce it 0.6 nanometers.
Oh, okay, 0.6. I'd
You
rather
see,
say that.
you see how
0.6.
that, you see how that works?
Yeah, I have it down here, so I'll have to go
Okay,
back.
now we're not done yet. We're not done
Oh,
yet.
no.
Because I ask in this example, please convert it to micrometers. It's the example I gave earlier. It's like, okay, convert 24 inches into feet. Well, that's 2 feet. This is about what we're going to do here. So keep a look at the number line. Put your eye on 10 to the negative 9.
Okay.
I'm asking you to give the answer in micrometers. Now, if you look at the number line, micro is immediately to the right of nano.
Yes.
You see that?
10 to the negative 6.
Exactly. That is 3 decimal places to the right from nano to micro. You moved 3 decimal places to the right. Now, here is where a lot of students, and don't feel bad about this because it's confusing to a lot of students. We moved to the right 3 decimal places to get to micro. On your answer, on the piece of paper, this is the confusing part.
Okay.
You're going to move the decimal in the opposite direction. You're going to move it to the left. 3 places. So that means it's not 0.6, it's 0.0006 micrometers.
Okay, that is confusing because why are we moved 3 points to the right?
Because I specifically asked in the example to convert your answer into micrometers.
Oh, okay, I see now. So we have to move 3 decimals back to where we were
In
at.
order to get there, yes.
Got it.
Exactly.
That is confusing. Okay.
Yeah, because your 0.6 nanometers was correct. I just wanted you to label it as a micrometer. So you did. You moved the decimal place on paper, you moved it 3 places to the left. Because you went 3 places to the right on the number line. I know that sounds confusing, but that's how it works.
No, I totally understand, believe it or not, because you're asking me to find the micrometer, but
The micrometer equivalent.
to the nano, right?
And the reason, even though it's not part of the next exam, Horace, the reason I went into such detail on this particular topic, when we would be in a classroom and I could actually sit down with you and show it to you on paper. The reason I went into so much detail, everybody, is because when I asked you to convert everything into micrometers, let's just suppose for an instant here, everybody, that you had a big, huge room full of random objects, and you needed to accurately categorize all of these objects. So you would find some form of common description that fits all of them. Let's just say their height. Okay, so you're going to randomly pick, okay, everybody that's 5 feet goes over here. Everybody that's taller than 5 feet goes over there. Well, by making everything micrometers, it's like making everything in feet. You're either above or below it. So when I ask you to write all your answers in micrometers, it's easy for you to compare the two numbers and look and see, okay, that's a smaller number and that's a bigger number. When it comes to wavelength, the smaller that number is, the more dangerous it is to you personally. That is high energy. The smaller the wavelength, do you remember that relationship, energy, frequency, and wavelength? The smaller the wavelength, the more energy that waveform contains. This is why ultraviolet actually burns you. Infrared is the heat that you sense in your surroundings. And yes, it makes you feel uncomfortable, but it's the ultraviolet that does the nasty things to you because it's a much higher energy waveform and it's much smaller than the heat waveform. And so it just penetrates right through your skin, strikes whatever major organs happen to be in the way. And hopefully for you and everybody you might know, it doesn't do any damage. Sometimes it does. Okay. Horace, did that help at all?
No, it really did. I'm just got to go back and keep practicing it. I have it wrote down in step.
Yeah, like I said, you're not going to do any of this math problem solving on the exam, so don't worry about that. So what I admire is the fact that you're curious. I like that.
Yeah, I see it, and I have to know.
Okay. There's nothing wrong with curiosity. All righty, here we go.
Recording in progress.
Yesterday, I covered the topics of temperature and calories. And I sent you a PDF file about an hour ago. Some of you may have had time to already download it and take a look at it, and maybe not, but nonetheless, there it is. And it's a further description of temperature and calories. And a quick reminder, temperature is not a measure of heat. Temperature is a measure of molecular motion, okay? Calories is the measure of energy, heat energy specifically. And the definition of it was it's the amount of energy necessary to raise the temperature of 1 gram of water 1 degree Celsius. Okay, that's what a calorie is. Now, in the PDF file that I just sent everybody, I show you a diagram in there. And real quick, let me get this diagram out. Because I provided you examples of how this concept of calories works. And I am looking at this page. Okay. That diagram describes what is called the phase transition of water. Now, don't be confused by the title, everybody. Phase transition of water merely means it describes the physical process that water goes through when it changes state from a solid to a liquid to a gas. That's what phase transition is. Okay, you're transitioning into another phase, solid, liquid, or gas. Okay. Now the diagram and all the numbers that are presented in this handout apply only to water. However, for every known substance, iron, aluminum, oxygen, fluorine, argon, you name it, any one of the 92 naturally occurring chemicals on the chemical periodic table has its own version of a phase transition diagram. And the reason everybody's different, everybody, is because obviously water boils and water freezes at different temperatures from, say, iron. Iron does not vaporize until you start approaching 1,000 degrees. Water does that at 212. So the diagram and the numbers associated with it are different for each element. So once again, the numbers that you see in this diagram only apply to water. And it should make sense to you now. Why water? What are we focusing on here? Well, this is the source of rain. This is the energy, because these storms that occur on the surface of Earth, everybody, they require energy to perform whatever it is they do. In the case of hurricanes, they need energy. And where do they get this energy from? And basically, they're drawing up the energy, and I know this sounds strange to you, from the oceans itself. The hurricanes that strike the southeast United States, Florida, the Carolinas, the Gulf Coast, Mexico region, those hurricanes, they originate over the Sahara Desert. You have a large body of, as you can imagine, hot, dry air. It's going to pass, that wind or that air is going to pass over the Sahara Desert. And once again, very dry, very hot. It's going to pass over warm equatorial water. And so the air above it is basically going to be like a dry sponge. It's going to soak up the water from the surface of the ocean right there, because the water temperature at the equator, everybody, is quite warm because of all that solar energy. Water contains energy, everybody. It takes energy to change water from a solid to a liquid to a gas and backwards. And so the longer a hurricane sits over an ocean, the bigger it gets, because it's soaking up the moisture from the surface of the ocean, and all of that moisture contains energy. And this is what the subject we're getting into in this section of material. That's what the phase transition is all about. Exactly how much energy are we talking about here? Well, this diagram and the math examples that I provided along with them should give you some clue as to the magnitude of the amount of energy that goes inside of a hurricane. It's absolutely astounding. We don't have nuclear weapons powerful enough to equal all the energy that's tied up in a large hurricane. And this phase transition diagram that I've provided for you gives you a sense of just how much energy we're talking about here, okay? And this is basically the water cycle on planet Earth. It goes from a solid to a liquid to a gas. It's one of the very few substances on this Earth that can exist in all three states of matter. We have ice at the polar region. Obviously, our oceans are liquid, and water vapor is in our atmosphere. So you have water in all three states. You don't see that in iron, for instance. Yeah, iron's a solid, it's in the ground, but when was the last time you saw vaporous iron in the atmosphere? You didn't. So water's one of the unique characteristics or features of water, at least here on the surface of Earth, is it's one of the few substances that's found in all three states of matter. And there is a physics, it's a rule, okay? It's has to do with the third law of thermodynamics. You cannot create energy and you cannot destroy it. I think I brought this topic up with you once earlier in the beginning of the semester. You cannot destroy matter and you cannot create it. That's a rule in physics, everybody. That's not religion. That is a rule. And what exactly does that mean? Well, I think the example I gave you was the table that you're all leaning against. That table contains energy. It takes energy for all those molecules that make up that table to hold it all together. And when you set fire to it, you are breaking those bonds. And yes, the form of the table disappeared. It no longer looks like a table. It's a pile of ashes. But the molecules are all there still. You haven't destroyed them. All you've done is release the energy required to hold everything together. And when you released that energy, you perceived it in the form of heat. Water goes through the same thing. So when surface water is drawn up into a hurricane, it becomes vaporous. Water vapor contains a lot of energy. And one way to illustrate this to you, everybody, what hurts more, a pot of hot water or getting hit by a bunch of hot steam? Yeah, the steam is going to hurt a lot more. Why? Because that water contains that much more energy. All of that is trapped in a hurricane. And that's what gives hurricanes their high wind speeds, is all the energy that the hurricane is drawing up from the oceans. Once that hurricane strikes dry land, everybody, that's when the hurricane begins to die. And the reason is it's over dry land. It's been cut off from its fuel source. It's no longer able to draw moisture up into it anymore. So all the energy that it contains when it hits dry land is going to get, unfortunately for the people in that area, all that energy is going to be released back into the atmosphere right over wherever it happens to pass over dry land. And so that hurricane is going to die in about 24 to 36 hours once it hits dry land. And water is an integral part of all of this. Water is necessary to agriculture here in the Central Valley. So what the conclusion of this section of material is going to end up being, just so I can give you some direction, okay, why are we having to know all of this? Well, at the end of this section of material, everybody, and leading up to exam 2, why is it necessary to know all about rainfall or temperature? Because it's the average annual temperatures and it's the average annual precipitation numbers in a given area that determines what is going to grow naturally. Agriculture is not natural. So here in the Great Central Valley, because we don't get a whole lot of rain here, and because even though this may sound strange to you, especially in the last week when it's been 110 degrees, but the average temperature here in the Central Valley is actually quite comfortable, like 67, 68 degrees. And when you got a combination of that kind of average temperature with the fact that we get very little rainfall, the only thing the Central Valley is capable of growing on its own is tule grass. That's it. All those oak trees scattered all throughout the city of Visalia are completely unnatural. They don't normally grow on the valley floor. Why do they survive? Because we water them. We protect them from predators, and we think they look nice. So here they are. But if it wasn't for us, those trees would die, because the valley doesn't have the rainfall or the temperature range for these kind of trees to survive on their own. And so this is why I'm going over such subjects as the temperature and calories and the phase transition of water. Okay, so in the diagram that I showed you just now, this one, okay, the diagram itself is labeled with letters. If you see that, there's A, B, C, D, and E. On the, I want to explain what those letters mean here right now. The A portion of the graph is in the lower left-hand section of the graph. It's a short line, it's angled, it's labeled letter A. Anywhere along that line on letter A, everybody, water is a solid. Water is a solid. Then notice that the B line is flat. A brief explanation of why it is, everybody. Let's just suppose that you had 1 pound of ice, or let's say 1 kilo of ice, and you've got it on in a pan on top of your stove, and your intention is to heat it up, melt the ice, and then warm the water up. So when you turned on the flame, if you had the ability to take the temperature of the water in that pot, what you would notice, everybody, is that all the energy that is being put into melting that ice, it's not increasing the temperature. The water is still 32 degrees. The water temperature will not begin to increase until all of that ice has been converted to a liquid. Then the temperature begins to rise, because you're putting in energy to cause that ice to go through a phase transition. It's changing from a solid to a liquid. Once that process is complete, now you can keep adding more energy and make it hotter, hotter, hotter. This is why the B portion of the graph is flat. All the energy that you are putting into it is merely being used to change it from a solid to a liquid. That's it. And because water has known chemical properties, there is a very specific number involved in the phase transition of water from a solid to a liquid. It's 80 calories per gram. So if you have a 2 kilo block of ice sitting in your pot. That's 2,000 grams. It's going to take 80 times 2,000. So it's going to take 160,000 calories to change that water from a block of ice to a bowl of liquid. That's how that portion of the graph works. Now, on the C portion of the graph, water is liquid all the way through the C portion of the graph, because if you will notice, at the bottom portion of the C section, you are at 0 degrees Celsius. And the top portion of the C section of the graph, you are at 100 degrees Celsius. So you're going to input energy, more energy, more energy. You're going to heat this pot of water up. And now all of a sudden you're at 100 degrees Celsius. The water is going to go through another phase transition. This time it's going to go from a liquid to a gas. However, it's going to require a little bit more energy to make that transition. So you still have 2 kilos of water. And you still have to change states of matter from a liquid to a gas. And if you look at the diagram, it says in order to do that, you got to input an additional 590 calories per gram. So if you take 2,000 and multiply it by 590, okay, I think you get something like 350,000 or 400,000 calories to go from one side of that D portion of the graph to the other side. The temperature will only begin to increase once every drop of water has now become vapor. Then the temperature will increase. And this is why steam hurts so much more than just ordinary boiling water. Boiling water is somewhere in the middle of the C portion of the graph. Steam is all the way up towards the E portion of the graph. It hurts a heck of a lot more. Now, as we went up the graph from A to B to C to D to E, we were inputting energy. We had to keep inputting more and more and more and more energy, so that by the time you got from A all the way up to E, you were putting in a grand total of several million calories in order to vaporize 2 kilos of water. Can you imagine how much energy is locked in over a hurricane as it passes over Florida? In this particular case, my example, you had 2 kilos of water. How much water do you suppose is tied up in a hurricane? A lot. And so you get some idea of the energies involved here. There's more energy tied up in a hurricane than there is a nuclear weapon. The difference is the hurricane releases its energy over a period of time. The hurricane or the atomic bomb does it all in about 2 seconds. That's the only difference. However much energy it took to vaporize 2 kilos of water, let's just say it was 3 million calories. You had to put 3 million calories into that block of ice in order to vaporize it. You can reverse the process, everybody. Remember, you can't destroy energy and you can't create it. And you can't destroy matter and you can't create it. The water is still there. And there's all kinds of energy associated with it now that you've vaporized it. You can reverse the process, everybody. If let's say you raised the water temperature up to 130 degrees Celsius, which is on the E portion of the graph, and you had to put 3 million calories into it to get it to go from the A portion all the way up to the E portion. When you reverse that process and refreeze that water and turn it back into a solid, you are going to release precisely the same amount of energy it took to vaporize it. You can't destroy energy and you can't create it. If it took 3 million calories to vaporize that water, that's exactly how much energy you will get out of it once you freeze it. Have you ever noticed that when you put food in your refrigerator, if you've ever moved your refrigerator in your kitchen, everybody, had you noticed that the coils in the back of the refrigerator were pretty hot to the touch? We're talking about a refrigerator here. So what's going on? Well, it's simple heat transfer technology, everybody. What that means is you're putting the food, which is at room temperature, let's just say that's 80 degrees. The inside of your refrigerator is 38 degrees. So your food contains heat energy. Energy only moves in one direction, everybody. It only moves from areas that are hotter toward areas that are colder. That's another rule in physics. Light only moves in one direction, from wherever it's lighter toward wherever it's darker. Okay? So you have the heat energy from your food. It wants to escape outward because the surrounding environment is now 38 degrees. So in this particular way, your food is going to cool down because it's attempting to heat up the refrigerator. You have a fan in your refrigerator that circulates the air. And where does that air go? It is cycled through those coils in the back of your refrigerator, whereupon the heat in that air is dissipated into those coils and returned to the refrigerator as cool 38-degree air. And that's where the heat from your food ends up, in those coils behind the refrigerator. Does anybody have any questions so far about that graph?
Yes, what was E again? I know D was liquid to gas.
E is the gaseous state.
Gas-ish state?
Gaseous, yes.
Oh, gaseous.
Yes, the A portion is solid, the C portion is liquid, the E portion is a gas.
Okay, thank you.
And that's true for any substance. The only difference is, if you can imagine, Veronica, it took it on the B portion of the graph to go from one side to the other, you had to put in 80 calories per kilo. Or per gram, I mean. Now, suppose you had a chunk of iron. It's going to take a lot more energy to get that piece of iron from one side of the B portion of the graph to the other side. Don't you agree? It's going to take a lot more energy to turn that solid iron into a liquid than it would water.
Yes, of course.
So the numbers are going to be different, but 80 is the number for water. Okay, that's what it takes to change it from a solid to a liquid. Okay, and when you put the ice cubes in your drink in your backyard, you're sitting with friends and whatnot, and those ice cubes begin to melt. Well, the surrounding liquid in the I mean, I know this sounds kind of nerdy, but it's physics, and this is how it works in this section of material. The liquid in your cup is warmer than the ice cube. So it wants to warm up that ice cube because energy only moves in one direction, from wherever's warmer toward wherever's colder, and the ice is colder. So all that heat energy is going to be basically absorbed by that chunk of ice. And over a period of time, it's going to be enough energy to make that block of ice in your drink phase transition from a solid to a liquid. There, how's that for nerd speak? Okay. Now, on the study guide, I've covered temperature scales, and now I have finished covering the phase transition of water. But the only kind of question that will show up on the exam is you're going to need to know, for instance, the heat of fusion is 80 calories per gram. And you're going to need to know that the heat of vaporization is 590 calories per gram. Okay? Latent heat. Latent, the word latent you can feel it, but you can't see it. It's latent heat. And so latent heat, which is trapped in water vapor, oftentimes when meteorologists describe the energy associated with a hurricane, they describe it in terms of how much latent heat there is in that hurricane. Hidden energy that they can't actually see, but they can see its effects by high wind speeds and the destruction that's occurring on the ground, but they can't actually see the energy itself. So it's latent heat, and it's the energy required to keep water either a liquid or a gas. Once you reverse that process, all that energy gets released into the atmosphere. Have you ever noticed, everybody, that it doesn't happen very often here in the Central Valley? So maybe you've experienced this in some other region of the country. It's a nice, warm, either spring or summer day, and it rains. Or maybe, let's say it's an early spring rain, so it's still a little chilly outside. It's maybe 65 degrees outside, but a little rain happens to come by. Have you ever noticed that when the rain is done and passes by, the air feels warmer to you? Have you ever noticed that? Because as it rained on you, everybody, all that water vapor that was in the air was reverting backwards into a liquid, and it was releasing 590 calories per gram into the atmosphere, and it warmed up the air. And so after it finishes raining, immediately afterwards, before the wind has a chance to blow it all away, if you walk out your front door and actually take the moment to, think about feeling the air, it actually feels warmer to you. Okay.
Is that why Arizona has monsoon season and it's warm?
Well, monsoon is an Arabic word, and it merely means reversal of the wind. That's all monsoon means. So the reason it has negative connotations is because it's unpredictable. And so for the most part, wind that passes over Arizona is coming from, it swirls around parts of California and southern Nevada before it passes over Arizona. And so basically it's dry air to begin with. There's no water in that region of Nevada, California, anything like that. So the air has no chance to pick the moisture up anywhere. It's dry air, and people in Arizona get these tremendous heat spells. But occasionally during the monsoon season, wind comes from a different direction. And if it happens to come right off the Gulf Coast, like say Baja or something like that, there's moisture over there. There's the Gulf there. There's the Pacific Ocean. It picks up a lot of moisture. And then it passes over Arizona. And it's unpredictable. That's why it has negative connotations. It's unpredictable. Here in the state of California, we have a similar phenomenon. It's called the Santa Ana winds. Firefighters hate this stuff. And the reason is that over the state of California, for the most part, the wind blows from the region of the Pacific Ocean towards New York. It's a westerly wind. It goes from the coast of California and blows towards New York. And that's pretty consistent, 24/7, 365. But occasionally we have these monsoon winds, which means that they're coming from the direction of Nevada. And that's very dry. And as it passes over the Santa Ana Mountains, if there happens to be a forest fire, you now have a big, huge body of dry air about to pass over that and feed the flames. So firefighters hate this stuff. But California has its own version of a monsoon wind. So yeah, that's all it means, a reversal of the wind. And why is it so dangerous? It's unpredictable. If we can't predict something, it's dangerous. Okay, states of matter. I've so far briefly covered that. That's solid, liquid, gas, okay? Amongst the pages in the handouts that I sent you earlier today, I have a diagram in there that looks a bit like this. Okay. And it's a quick overview of how much energy it takes to go from one state of matter to another. Please notice on the top of the diagram, there's one up there that so far I have not mentioned to you, and it's called the process of sublimation. Virtually any substance known to man, and water is no exception, there is the ability to completely bypass the liquid state. In other words, you can take solid water and convert it directly into a gas. When you do that, the process is called sublimation. Now, once again, you can't destroy matter or energy, and you can't create it either. So if you'll notice on the line there, when it comes to water, it says that sublimation is 670 calories per gram. Well, if you look at the two numbers between the boxes, 80 calories and 590, if you add those two numbers up, you get 670 calories. So there's no magic here. It still takes 670 calories. However, you can sublimate water. And when you say sublimate, that means you are bypassing the liquid state. Doesn't matter what the substance is. It could be iron, it could be anything. If you sublimate it, you're bypassing the liquid state. You're either going directly from a solid to a gas, or you're going backwards, directly from a gas back into a solid. But you're bypassing the liquid state. And in the case of water, in order to do that, you need to input 670 calories per gram. Okay? The process when you go from a liquid to a gas is called evaporation. And the reverse process is called condensation. Okay, you've seen condensation in your own bathroom when you turn the shower on. The steam condenses backwards into a liquid on your mirror. And it released all that energy into your bathroom in the process of doing that. And so your bathroom got really hot. And you had to open the door and hope to God your little brother or your little sister go running in there and bothering you. Okay. So after that, we have atmospheric gases, and that'll be the last topic for today. But atmospheric gases, in actuality, the air that you're breathing contains dozens of chemicals. However, fortunately for us, the vast majority of them are found in trace quantities. They're barely a statistical blip, so we're not going to mention all of those. I'm only going to bring up with you 6 different chemicals. 3 of them are fixed, 3 of them are variable. First, what does it mean to be a fixed gas? If you sampled the air around your own house, and then if you had the ability to sample the air in Australia, and then sample the air in Siberia, okay, you would not only find the same chemicals, you would find them in the same ratio. That's what it means to be fixed. They're in the same ratio. That doesn't change. And here's what I mean. There are 3 fixed gases. The most common gas in our atmosphere is nitrogen. Nitrogen chemically in our atmosphere is N2. It's N with the little subscript 2 underneath it. Okay? It makes up 78% of our atmosphere. No matter where you go on this earth and take a sample of the air, the nitrogen will always read 78% because it's fixed. Nitrogen is responsible for the color blue in our atmosphere. You've got 2 atoms of nitrogen bonded together to create N2, which is what our atmosphere is made up of. Each of those atoms, now that they're combined with each other, everybody, they do have a physical size to them. It's incredibly small, but they do have a physical size to them that can be measured. And it just so happens that the length of these nitrogen molecules is pretty close to the equivalent of the wavelength of the color blue. So basically, nitrogen is tuned to the color blue. So when we look up in our telescopes and we see a planet far off in the distance, and the only thing we have to measure of the darn thing is its color, well, if it glows red, that has to be hydrogen. If it glows green, that's got to be oxygen. If it has a bluish tinge to it, that's got to be nitrogen. And that's how it is in our atmosphere. Nitrogen is also inert. That's spelled I-N-E-R-T, inert. This means that chemically, nitrogen does not like to, at least the N2 that's in our atmosphere, does not like to combine with other substances. It's perfectly happy on its own. And that's a good thing for us, because when you take a breath of air, everybody, yes, you're inhaling the 78% nitrogen. However, it's not interacting chemically with anything in your lungs. You're merely exhaling it back out. Think of it as filler. It's filler. It's also providing the pressure on this planet because it makes up 78% of our atmosphere. So it's a very significant contributing factor to what the pressure is here on the surface of Earth. The second most common element, the second fixed element I need you to know, is oxygen. Oxygen makes up 21% of our atmosphere. And unlike nitrogen, it's not inert. Oxygen is reactive. That's the opposite of the word inert, reactive. Oxygen is also found in the form O2. You cannot breathe just O and live for very long. You cannot breathe O3 and live for very long. It has to be in the form of O2. And it is very reactive. When you inhale, the oxygen reacts with the heme in your blood cells to help with the hemoglobin in your blood. It also interacts with other parts of your body to contribute to the digestion of carbohydrates. So it reacts chemically with your body, and we need it to survive. Makes up 21%. Yeah. The third most common element in our fixed category here, everybody, is argon. Argon is a noble gas. Like nitrogen, argon is inert. It doesn't combine with anything else. So when you inhale it, it merely comes back out when you exhale. Okay. It makes up the remaining 1% of those numbers. If you add up those three numbers, everybody, they come out to be 100%. The variable gases are all found in trace quantities. I am not going to give you a number associated with them because obviously it's all less than 1%. And I don't need you to know that something is 0.0056%. No. But in the variable category, everybody, what this means is because it's variable, the ratios are going to change depending on where you are at. So depending on whether you're standing at the equator or at the polar regions. In the variable category, there are three chemicals I want you to know. The first one is carbon dioxide. It's CO2. Carbon dioxide is also the greenhouse gas. Now, you've seen the subject of greenhouse gases in 6 o'clock news, no doubt, over the last couple of years and how important it is towards global warming, and it is. But keep in mind that I'm about to tell you that, it's found in trace quantities. So why is it making such a big deal here in the 6 o'clock news? Because it's that significant. It doesn't take a lot to drastically alter the environment on Earth. To give you an example of what too much CO2 in the atmosphere can do to a planet is all you got to do is take a look at the planet Venus. Its atmosphere is made up predominantly of CO2. And as a result of that, everybody, the temperature on the surface of Venus is 900 degrees. And the surface pressure on Venus, and because of the CO2, is 90 times what it is on Earth. So if you were to somehow magically transport yourself to the surface of Venus, within a second, you'd probably be crushed and then baked instantaneously. But the reason we study Venus so much is because we want to know what the greenhouse gases can actually do to a planet. And Venus is a good example of that. So it's found in trace quantities here on this Earth, but if it increases even up to say 1% or 2% of our atmosphere, the average worldwide temperature on Earth is about 56, 57 degrees. And if you increase that temperature, the average temperature, say up to 65 degrees, that sounds comfortable to you, but you got to remember it's an average. This means some places on Earth are going to get way, way hotter. So anyway, carbon dioxide is the greenhouse gas. It's in trace quantities, and it is, excuse me, it is it is pretty unevenly distributed around the planet. So I'm not going to give you an area of concentration. The second greenhouse gas I want you to know is ozone. This is chemically, it's O3. It is concentrated over the polar regions, and it is responsible for blocking much of the ultraviolet light that gets through the Earth's magnetic field. Earth's atmosphere is thinnest over the polar regions. It's thickest at the equator. From the ground up at the equator, our atmosphere is probably 80 or 90 miles thick. Once you get to the polar regions, that number decreases. It's probably about 40 miles thick. And what this means is solar energy can penetrate deeper into our atmosphere. And when it does this, this is ultraviolet light, everybody, and you now know, excuse me, that ultraviolet light contains a lot of energy. It's going to collide with oxygen molecules at the polar region, and it's going to literally energize them and turn them into O3. And when it energizes these oxygen molecules in the atmosphere, it makes them glow. and oxygen glows green, everybody. And this is what you call the aurora borealis. It's solar energy that has penetrated deep into our atmosphere, and it has collided with oxygen molecules over the polar region. And it has passed that energy onto the oxygen molecules, causing them to glow. And in the process, it creates ozone. The third variable gas I want you to know is water, H2O. It's concentrated mostly over the equatorial regions. For human life to exist over a long period of time, everybody, you need a certain amount of humidity in the water or in the air. You cannot continue to breathe completely bone dry air day after day, month after month within about a short period. And I'm talking only about maybe 2 to 3 years. Your lungs would dry out. And if I put a stethoscope on your chest, everybody, your lungs would sound like a dried leaf to me. So you need a certain amount of moisture in the air, if for no other reason than your own health. Okay. One of the reasons the Great Central Valley has one of the highest rates of asthma and bronchitis is the air quality here in the Central Valley is not very good. You live in a box, you're completely surrounded by mountains. And of course, all the farmers in the area here, it's not a fault, everybody. It's just, that's what it is. They're going about their business, taking care of their farms, but they're also kicking up an awful lot of dust. And there's no place for that dust to go because we're surrounded by mountains. And so the air quality here is not the best in the world. And it's a desert, so the air is pretty dry. So you have this dry air combined with all of this agricultural waste that's in the air, and we end up with the nation's leading per capita asthma and bronchitis rates. Okay, does anybody have any questions so far?
Recording stopped.
Okay. Once again, if you go over the handouts and you have questions, please feel free to email me, okay? And if nobody has any further questions, I will see you guys next Tuesday.
Can I get the handout today or you?
I sent it about an hour before class started. Yeah.
Not the handout, excuse me. I'm talking about the recording because that's how I make
Oh,
my.
yeah, that'll be ready in about an hour.
Okay, thank you.
Yeah, I'll send it.
When you were talking about the moisture in the air, is that why like red light saunas or saunas are like make you feel regenerate? Yeah, I'm saying it wrong. Where your lungs just feel really good when you're breathing that in.
Yeah, you know, when we hook patients up to a ventilator in the hospital, that's one of the considerations. If, you know, we can't just pump dry air into their lungs. That would be very harmful to them. So yes, we have to humidify the air as it goes into them. And when you're in that sauna, you're breathing humidified air. And I know you're probably familiar with this. Your lungs are basically like a sponge. And so when they dry out, they lose that elasticity, that easy ability to give and take with the pressure in your lungs, right? And that's why sometimes when you know, if like say you were a smoker or maybe you just, you know, you've lived all your life in a dry air environment, yeah, that's why it feels it's a little easier to breathe because you're basically softening up your lungs.
It's really cool. And
Yeah, you should see the, you know, and it's amazing. People freely choose to smoke throughout their entire life. You know, when you're putting dry smoke into your lungs, is it any surprise people develop respiratory issues? So,
And then,
pardon? Sure. Sure. Is water is what now? I didn't understand your question. Water is what again?
If it freezes, yeah, I think.
What was the original? I wasn't understanding that last word.
A solid. He said water is also a solid.
Yeah, it's found in the solid form on this earth. The polar regions are solid water. And yet we have liquid oceans. And then, of course, we have water vapor in the air. So water is one of the very few substances on earth that exists in all three states of matter. And the reason for that has to do with the unique pressure and temperature characteristics here on the surface of Earth. You know, we have a air pressure that is just so much, and then we have average temperatures which fall into a certain range. And all of that contributes to the fact that water can exist on the surface of Earth within all three states of matter. So the range of temperatures that you find here on this earth all fall within the ability of water to exist within the three states. If you lived on the planet Venus, the temperatures there would be ripe enough to liquefy iron. It actually rains metal on Venus. Venus does not have a water cycle like we have, you know, where water goes from the oceans up into the clouds and then back down again. Venus has that, except it's in the form of metals because it's so damn hot over there. You know, you've got temperatures hot enough to melt iron. So the iron is already in a liquid state. Any further increase in temperature and you keep putting more and more energy into that iron, and you will eventually vaporize it. And then as it rises up through the atmosphere, it will condense backwards into a liquid again, where it will fall back down on the ground. Is that weird?
That is very weird and interesting.
But my point though is that remember me telling you yesterday, the physics is physics, doesn't matter where you're at, it's all the same, you know? So that's why it's so important that, you know, the better we understand how this earth works, the better we understand how other planets work. And likewise, they teach us lessons too. Venus is completely covered in greenhouse gases. So we have some idea of what that can actually do to Earth by studying Venus. We also understand much, much better the importance of a magnetic field because, Venus does not have much of a magnetic field and neither does Mars. And yet both of them, one of them, its atmosphere has been nearly stripped away by the solar wind over the millions of years. The atmosphere on Mars is only 10% of what it is here on Earth. So, and it's made up mostly of CO2, not oxygen. And so, the atmosphere thins out within about the first, if you on the ground on Mars, if you go upward just 6 feet. So the difference in air pressure between my feet and my head would be so much that I'd probably explode. And then when you go to Venus, it's the exact opposite. The atmosphere is so heavy there that the pressure is 90 times what it is on Earth. So what we learn and understand about how the Earth works teaches us about other planets, and then likewise what we see happening on these other bodies out there teaches us how the Earth works. So we are no longer of the opinion that Earth is unique in the solar system in regards to meteor impacts. We've been hit and we've been had life completely wiped out on numerous occasions throughout the history of this planet. The dinosaurs were not the first, and unfortunately they won't be the last. So yeah, we've new technology is allowing us to see the bottoms of the oceans as if the water wasn't even there. We can see underneath the Sahara Desert. and we can see that the Sahara Desert used to be a tropical rainforest. So pretty cool stuff. All right. I went to bed early last night. It's amazing what a good solid 8 or 9 hours of sleep will do for you. Now I'm the Energizer Bunny.
I have a quick question. I sent you an email in the beginning of the week. I'm going to be in San Diego for a week, and I won't have access to a printer. Can I either have I know not the whole quiz or the exam, but can I have the paper that you want us to fill out, or can I just write 1, 2, 3, 4, 5, and then the letters and answers on a piece of scratch paper? Because I'm assuming that we have an exam that's coming up Thursday.
Most likely, yeah. All right, you just need the answer sheet. I'll
Yeah.
send you the answer sheet plus the remaining handouts for this section of material.
Okay, awesome. Thank you so much. Yeah, I leave Saturday, so if I can have that to print out by tomorrow, maybe.
Sure, okay.
Okay, awesome. Thank you so much.
Bye-bye.
Have a great day.
Bye.
Thank you. Bye-bye.